Any questions in the audience? Okay.
I'm an economist in training, but I'm pretty skeptical of the economic toolkit. I'm kind of curious on how you guys are approaching what you're framing as, economic questions or economic systems to model. But the usual analytical toolkit that economists use in their academic papers of modeling specific utility functions or constraints based on real-world objects. I don't really see in your system modeling. It's more of a system engineering approach. So I'm not pushing you to answer it one way or the other. Just tell me what your view is. But do you see value in adding, for example, in the equations that you laid out, saying distributions and their simple discrete steps of how they evolve? Do you see value in adding specific functional forms to some of those equations on trying to model more of the specifics of people get money from doing this specific transaction, or I think their utility would follow this rough functional form? Yeah, do you see value in specifying things in that more detail? Or more traditional econ approach? I can answer, but you can start, whatever.
Okay, sure.
Curious from anybody.
Yeah, I think we should probably give you multiple answers because I don't know that we all have the same one. My answer is that I largely view economics as a domain and that engineering as tools. So when economics has certain knowledge, then we can use the tools to sort of test them as assumptions. Largely any representation of a system is an assumption. So the reason you would use sort of stochastic dynamical systems and various forms of computational science is to combine those assumptions with sort of real data and start to look at how well they bear out in practice. And you see a very large mixture of things from, heuristics based on behavioral economics all the way to implementing reinforcement learning, which is a form of stochastic optimal control on the part of the agents to basically allow us to find from a big toolkit in a particular problem what's actually helping us make design decisions, which I think the key here is that ultimately you're making decisions, and which tools you end up using is really defined on what facilitates that decision making, and then over time we'll improve our understanding of which decisions resulted in the desirable outcomes. Although we have a lot to build on from the past, we also are sort of moving into frames where I think we are opening up new problem classes where we have to address how we carry tools forward from the past and learnings forward from the past and mix them with sort of new ideas to construct maybe new economic models that will eventually be the very things the people in your boat have to learn 10 years from now.
Yeah, this is a very good question because this is actually how we guys met, so Michael and I, because 1 year ago I started digging into cryptoeconomic research, and I started with the DSGE model, so Dynamic Stochastic General Equilibrium model, and Michael told me, you're right about the dynamics and the stochastics, but you're not right about the general equilibrium. And this is where we wanted to apply the utility approach for representative agents and so on and so on. But we recognize that it's much more complicated than that. So agreeing with you. So now, since we have the methodology and since we have the computation, we should use it. We could improve economic theory. The other thing is that we also had a cryptoeconomic seminar this semester for PhDs at our university, where we were talking with our economists, with our finance guys, with our business guys. And what you can see there is, so the papers that they approach, or the cryptoeconomic thinking they apply, is you have the economy and then you put in one cryptoeconomic thing, right? So they ask questions like, how would a cryptocurrency influence our economy? And they are not talking about how to design a crypto economy. Yeah, so this is one of the main things. Then on the other hand, a third answer to your question is that I was talking about different scales, and on the very fundamental micro layer, on the micro foundations for the economy, might really be modeled or investigated using utility functions for agents, right? So this is possible, but the further you zoom out, the more you need to have this systemic thinking. And what Shermin will tell you probably now in her answer is that we have we have this is Hayek thinking, right? So 40 years ago, we have the system theory cybernetics, but this hadn't. This is your answer, so you should be able to.
This is an interesting turn of events here. No, I wasn't going to say that, but I think you should continue that.
So economics, like as I said before, has like 250 years of history. And at some point in time, we restricted ourselves to what we can understand and what we can observe and what we can compute, right? So at some point in time, we got into this direction. Okay, we understand this world and we can make conclusions about what we see. And now, since we have computation and since we have these digital economies, we can basically go back into this point in time where we can restart and maybe apply things, as I've shown in my videos, like as we do in robotics, right? So maybe you could do this.
So maybe, economics, referencing to the slide that Kris showed, there are so many schools of economics. There is not one school or thought of economics, and there are so many approaches, including what we call heterodox approaches, which in themselves are so diverse also. And really it is about finding the right approach. This is what I said in my talk, is like we need to identify the right domains and kind of the disciplinary parts of different disciplines. Within economics, we have so many. Economics in itself is interdisciplinary, right? So a certain school of economics could have certain methods or a perspective that could be useful for what we're trying to do, and we identified that in Hayek's writings, in Ostrom's writings, for example, right? So what we're trying to do is apply it, and it's a highly iterative process. So what Kris walked you through was the process we're living at this research institute, because it's interdisciplinary. Like, we're working with Michael, then we make assumptions and models, then we go to our macroeconomist, he feedbacks to us like what he understands and where he would use different words. So this is this real big translation process that we're doing, because we're not on basically we're a distributed system in our institute, and each the state of knowledge of each of our researchers is different, and they have a different language system that they use. And what we're doing now, and this is cost intense, is synchronize our state of knowledge, including the vocabulary. And this is costing us time, and we're just at the very beginning of this process.
Tarun needs to go, so I want to let him answer.
Sorry.
Yeah.
I'll just. I got another mic somehow,
Okay.
but thanks. I guess I'll just give a very more concrete answer. I think from a practitioner standpoint, you do use different scale modeling. Like, if I'm doing a StatArb portfolio where like I'm doing equity rebalances, I will not model every UDP packet that I get from an exchange. But if I'm doing like market making on futures, every single packet and timestamp completely dictates the value of the like next expected value of the contract. So you do end up having to model something like aggregated utility functions, which, in options pricing, you model the price feed. So like, maybe you say it's a geometric Brownian motion. Maybe you say it's like something with a jump process. Maybe you say it's something that's not Ito adapted, ... whatever. There's a lot of ways of doing that. But you try to like figure out what scale maps most reasonably to what the participant's view of the data is. So like in options pricing, the participant's view of the data is like the underlying price, and then like what strikes have any non-trivial liquidity, versus like in futures pricing, the data is like the true ledger. Like, order books are just ledgers, right? So like everyone has their own copy of the ledger state, and you're trying to guess what the deviation between your ledger state is and the exchange's ledger state and what you think the other participants' ledger states are. And in that case, you do try to model the utilities, but you always add in. So one of the reasons I brought up all the algorithmic game theory results is algorithmic game theory is a study of game theory under the assumption that you need to compute something efficiently, or like, what's the theory for whether you can do that or not. And a lot of the impossibility results in algorithmic game theory kind of tell you have to do an approximation and it's not going to work out perfectly. So you try to do the best you can when you have to choose utility functions that way. But a lot of it is like iterative, where you like choose one, see how well it works, and then, okay, you found some edge case, so now you like mutate it around that state, and like you slowly build up these like this utility function as a function of like conditional distributions that you're observing. At least from the practitioner standpoint, like taking crypto trading data or on-chain data, that would be like how you'd view this.
And just adding on to that, from a practitioner standpoint, like sometimes like the agent that you're designing, like we assume that the utility is within the system, but like in reality, sometimes some of these agents may have other utility outside of the system that it's not even observable. So that comes the challenge of how do you really like reconcile and try to model that.
I have one more question, I guess, for Tarun before.
Yeah, sounds good.
So you kind of mentioned in passing in your talk that you wouldn't want to apply like machine learning to these sort of problems, and I didn't really follow the reasoning.
I see. Yeah. So it's not necessarily that I wouldn't necessarily want to apply it. I think for things that high capacity models, so like a neural net or a boosted tree, when I say capacity, the capacity of a model is sort of like an approximation of either a VC dimension or a Kolmogorov complexity, something that measures like how complex the functions this model can represent look. And the problem with training high capacity models is it's very easy for them to get stuck in bad minima, and the ordering in which you train them, the ordering in which you feed data into them gives you different answers. And so there's lots of ways you can deal with that. But when you have a dynamic data set, like in trading versus in like ML, like traditional like tech company ML stuff, the data set of faces is not changing like a crazy amount per day. Like if you look at the growth rate of like new facial data, it's like there are new faces, but they're reinforcing existing like clusters of faces you've identified. Whereas in trading, it's super heteroscedastic, which means the noise distribution is changing every day depending on events. So like the Fed accidentally increases rates by 50 bips, like that's a completely different trading environment than 25 bips. So you need to like train models to like adjust to these different time variances, and using high capacity models to do that can often like lead you astray because you look like you're getting really good performance in test data, but then like when you actually run it in production, it doesn't work.
If I add something. So what's interesting about sort of machine learning models in general is they tend to be treated like they're magic boxes by people who don't apply them. So they have underlying mathematical assumptions, and the underlying mathematical assumptions make them good or bad at specific things. So in the engineering discipline where you're dealing with like robotics, automation, and control, you often have actual models of the system's sort of higher orders of evolution, whether it's estimates of the noise distributions, estimates of the system plant and how it evolves. For example, like even a simple spring mass system that you teach people with, you have you can relax the problem where you don't know the mass and you don't know the spring constant, and you are in time estimating those things in addition to adaptively controlling the system. And when you get into applying machine learning methods in these more complex systems with sort of changing noise distributions, with changing system parameters, with so on and so forth, you can't use them the same way that they're used in the sort of the big tech examples that they're generally taught in the context of like the facial recognition, and where a lot of the buzz about machine learning comes from is not consistent with solving dynamic problems as opposed to static data set problems. Cool. So we're going to take a break and thank Tarun because he has to go to DevCon now.